Well, I'm a physicist by education, but long ago. But 10 years ago, I just got interested in 3 data points that were announced after the elections over the radio. And then I draw a line. It was a straight line. Then I added more points. They were on the same straight line. Then I had some ideas. Well, as a result, we have, the so-called Špilkin method, which is actually a method of John Brady Kisling developed in Armenia. And we have a Churov's saw, which actually is a saw by Vishnikov or anyone else. So that's all we have. So I'm collecting election data from Russia and all over the world. First of all, election data is a giant statistical experiment already paid by taxpayers. So when you are not allowed to see them, you are losing your own money. You are deprived of your own money. So they are official, they are global, they cover difficult areas, which is very important for any electoral analysis. It gets better over time, because when you have a large archive, you have a history, you have interconnections, you have many additional. You have an additional dimension which greatly enriches the data. Well, again, they're multidimensional, and which the last point is very important. It takes little effort to obtain actually. If you need one programmer. If the data are published, you need only 2 programmers, 2 staff programmers, and you get all the data you need. Probably, I know that many people, many one-man enterprises collect this data. Like Alexei Sidorenko collects a large collection of electoral data, but on a different level. But his interest is primarily in electoral geography. So he draws maps. But if we are interested in analysis of fraud, probably we need a little different data, but we still can collect them quite easily. This was, in fact, what I did when I first got interested in this. Well, and some practical use for these purposes. What the standard phrase is that your observation does not prove anything global, and your statistic does not prove any violations. But actually, statistics and observation are complementary. Observation provides us with evidence, and statistics provides us with some estimates, with numbers. Well, and now I got a nice idea that I wanted to share with you. And first three examples of situations when purely statistical ideas allow us to estimate elections as fraudulent. First is a very nice case of presidential election in Syria in 2014, not because it is Syria, but because these elections were immediately after the Donetsk Народная Республика referendum. Because the DNR referendum, and many people got interested in the results of DNR referendum, which was falsified, and a Russian person, a Russian blogger called Roman Tumaikin found the results of Syrian presidential elections, and eventually he was cited by Andrew Gelman, is an eminent American statistician. He was cited in the Washington Post. Here is the results. You see that the numbers are calculated on a calculator. Just like Alexander Shen told before, but here you have more numbers and you have, a very significant several orders of reliability, several additional orders of reliability. All numbers are, all percents are round, actually. All numbers are calculated up to 1% with an accuracy of 1%. Another example, Belarus elections in parliamentary elections.
What was wrong with the previous slide? Yes, what was wrong with the previous slide?
The previous slide, because the percentages have zeros after these numbers, many zeros. Because as you see, the total number of voters, you multiply them by this percentage, officially announced, and you got the number of votes up to less than a single person. And 4 times like this.
So it should not be just 8.7 and 0, 0, 0.
8.7.
And then many zeros. Well, 6.
We better add zeros.
Yes, but actually these zeros were not announced. They were the data were published as this. No one wrote these zeros, but they're implicitly they're here.
Okay, so this was published.
Yes.
And when you calculate, you see a long line of zeros.
Yes.
Calculate.
Yes. Okay. The same situation with elections in Belarus. Quite enough numbers and enough accuracy, enough zeros to tell that these data are fraudulent too. And the standard classical example of elections in the city of Saratov, where all the results are just carbon copied between precincts. Well, and the idea that I have that election fraud happens at the reported level. If you report data or elections results at the country level, as in Syria, you falsify them at this level. If you report them at oblast or electoral district level, like in Belarus, you falsify them at this level. And if you publish them at present level, then you falsify them at present level, which has an important corollary. Access to lower level election data lowers falsifications to lower level of the society, of the system. So it is beneficial, actually. And it stimulates civil involvement. Because if you only have a result for the country, you cannot do anything. So the lower level data you have, the better chance you have to involve more people in the investigation. Well, and I think that my guess is that availability of present level data, election data in Russia, which was inherited from a pre-Putin actually era, is an important factor shaping the political system for some time, or for several years now. Well, okay, then why do we need lowest level data? Because in many situations, in many collections of data that we see, people limit themselves with districts or constituencies or anything like this, because it is convenient. You just see how candidates and results of candidates and districts. Okay, that's fine. But if you have any need for deeper analysis, you'd better have as lowest level data, because first of all, if we agree that data are falsified at the lowest reported level, then we need this lowest reported level to separate clean data from fraudulent data. And if we have clean data, then we have some reference to count against, to check other data against. Then also another important factor, then the more data you have, the better histograms you have, the better graphs you have, and you have more dimensions and interconnections, of course. Well, and just several examples of what we have. In Mexico, we have data at sub-precinct data, which is casillas, which is just boxes. And they are divided alphabetically, which is very important and very valuable. So people are divided between casillas in alphabetical order, so you can actually test several subsamples of the same population within a precinct. This is the best situation I know. In Poland, we have just Excel files. Okay, that's very fine. In Finland, we have a database, but now it has an export format. So, in Spain, we have a strange database dump in punch card-like format. It is 80-character strings. But still, they are precinct level. In Russia, we have precincts in web tables. Okay, it's collectible. In Czechia, we have a web page for each precinct. There are not too many, it's collectible. In France, the election system has data only over communes, and communes are very large, maybe very large, or are of very different size. So the whole Toulouse is a single commune. But I don't know why, and I don't know where they take this data, but precinct level data are available at efficient open data portal. Okay, that's fine. But not many people know this. In Turkey, we have precinct level data, but very difficult website to scrap. In Germany, we have precinct level data, but we need to order them by mail from the office, from an official office. In Moldova, we have precinct level data, but the data tables are pictures. They look like web pages, but when you try to copy the text, you find that they're actually pictures. In Italy, we don't have anything because all data are scattered around individual communes, there are thousands of them. In Belarus, there are no precinct level data. So the outcome is, well, we need to exert some effort to collect precinct level data, maybe, because there are different aspects in this. First is digital preservation. No one guarantees that you will have the same data at the same website after some upgrade, as it happened in Russia when some electoral data disappeared in 2007 or something like this. And all the elections are not available, and some tables have names that mean truncated. So they are intentionally truncated for 1996, for example. Independence of internal politics. So we need an international database. Well, over the time, the value increases and the cost lowers because storage becomes cheaper, computers becomes cheaper. So if we do begin it now, it will become cheaper and more valuable over time. And minimum human effort, again. If the data do exist, we can collect them and without too much difficulties. That's all. That was a call for action.
Хорошо. Значит, вот сейчас в нескольких выступлениях промелькнула одна и та же вещь. Я хочу просто назвать слово, которым это называется. Слово называется «робастная статистика». Только что упоминалось, что графики интерполяционных прямых в методе Собянина-Суховольского очень зависят от выносных точек, от аутлайеров. Только что Борис рисовал картиночку с кучей точек на главной зависимости и облачком сверху. Ну, две, неважно какие. Вот у меня есть группа точек, лежащих на одной прямой. И есть одна точка, которая портит все стадо. Для работы с такими данными есть стандартный аппарат, который называется рабасная статистика. Средняя арифметическая зарплата у коллектива из 10 человек с зарплатой 10 тысяч рублей и одного человека 100 тысяч рублей сильно отличается от реальной зарплаты этих 10. Для этого существует понятие медианы. Вот для такой конструкции существует понятие там, вместо метода обычного метода наименьших квадратов существует метод усеченных наименьших квадратов. Найти такую прямую, которая минимизирует сумму квадратов, сумму половины отклонений, сумму квадратов наименьшей половины отклонений. Вот. Пользуйтесь рабасными статистиками. Если у вас есть облако, вы видите облако, над которым висит снаружи какой-то мусор, и вы подозреваете, что это мусор, искаженные данные, отсеките искаженные данные, воспользовавшись каким-нибудь методом. То есть эту точку можно просто выкинуть, или найти там, применить правильный метод наименьших квадратов с минимизацией правильной величины. Он проведет вам точку сюда, выявит правильный коэффициент и правильно назначит эту точку мусором. Примерно то же самое мы делаем, когда рисуем вот эти самые графики с гистограммами. Мы видим облако. Вот если мы в координатах явка, результат, мы видим здесь какое-то кометное облачко и потом хвост. Вот. А здесь, когда мы его проектируем, мы видим сумму голосов за одни партии вот такую, за другие вот такую. По сути, мы выделяем некий кластер надежных участков, назначаем их главными, эти назначаем тем словом, которое называется outliers, выкидываем их, вычисляем правильный коэффициент соотношения голосов за прочие партии и за нашего административного координата по правильным точкам, а все остальное, принимая его за искаженные результаты, соответственно, вычисляем как разность. Нет, еще раз, обычные методы линейных аппроксимаций, все методы наименьших квадратов, все средние, неустойчивы к отдельным точкам, к отдельным выбросам, имеют нулевой порог устойчивости. Я могу одной точкой вытащить средние куда угодно. Я могу одной точкой испортить мне график линейной зависимости. Вот. Пользуйтесь правильными отсечениями, отсекайте лишние данные, там миллионы разных методов. Не забывайте. Все. All examples are from Baku, the city of Baku. Well, it's a capital, but still we know that a city is normally a rather uniform structure. Well, what we see here, we see turnout varying in very high range, and result is almost absolutely constant, 87.5%. Okay, another constituency in Baku. Narrow range of turnout and constant result. Another constituency, very narrow range of turnout and constant result. Another one, okay, some outgoing points. Okay, so what we see an unnatural concentration of results and turnout. Why it could not be? Well, the answer is if you have a set of independent voters, and each voter, well, let's imagine he draws dice in the morning. He throws a coin. Okay, a coin with a 75 to 25% coin. If it falls on the 75% side, he goes to vote. And on the other side, he doesn't want to go to vote. This is the best model, probably one of a possible model of independent voting. Okay, so, and the best we can say about the precinct that votes with a turnout of 75%. Okay, we can arrange a precinct that would vote with 75% turnout every time, but
you need some preparation to do this. You need to order people whether to go or not to go, or you need to specially cut the precinct of people, carve the precinct of people that are always voting or always non-voting. But all these constructions imply some influence on the voters before the voting. In some sense, in some general situation, you should expect some statistical dispersion of voting. If you hold multiple votings at the same site, at the same precinct with independent observers, you will have a dispersion of something like this. This is a binomial distribution, so-called. Okay. Similarly, for voters that vote, you have 750 voters approximately that went to the precinct and voting on average with 85% probability. Then you should expect a dispersion of 1% and 300 in both sides and something more. You will have a Gaussian distribution actually, essentially, around the average value. But you see that you don't have such dispersion here. It's much, much smaller. Okay, and overall. So, okay, what we can do with this? You can do statistical modeling. It's a bit similar, a little similar from the current news. There are processes going, anti-redistricting courts going now in redistricting courts going now in United States that are against gerrymandering in voting districts. And one of standard approaches used now by the people who initiated the processes is mathematical evidence. You try to cut different districts at the same population at the known results of election, and see what party will win and what will lose from these different districts. And it shows that in gerrymandered states, you have you indeed have the current gerrymandered districting is indeed favorable to the Republican Party in particular. So this is a rather standard approach. Okay, we take the same set of precincts with the same number of voters and the same average intentions, and hold many model election outcomes. And what we see here, this is the median number of votes received by Aliyev at the same voter intentions. This is the upper limit of Aliyev's number of votes for Aliyev in 1 million runs. This is the lowest number of votes for Aliyev in the 1 million runs. So you see that some points at the observed histogram are well beyond 1 million runs. Below the same, but you take the difference from actual minus median and divide it by the standard deviation. So this is 3 standard deviations, which means, well, 1 chance in 1,000 to go beyond, to go outside. So this is the border of 1 million runs, and these points are well beyond still, and these are well below. This is very much because you can tell there are several orders of magnitude additional with this sticking outside. So you may say that this histogram, this distribution of votes is absolutely impossible it could not be, it could not appear with accidentally, by chance. It has a very high p-value about which Alexander told which Alexander Shen discussed in the first day, and probably even with all possible corrections, it will survive with very high probability that this election is not natural. Essentially, this means that this distribution is too narrow in result. This is the effect of these concentrated results are sticking too strong from the overall dispersion. There is a paper on this regarding Russian elections, regarding the Churov's bird.
Окей. Спасибо, Сергей Александрович. Время. Или еще есть что сказать?
No, that's essentially all.